Okay, finally in this lecture 8, we are going to see how to solve partial differential equations with Fourier transforms and their properties. And we call this method, of course, as the Fourier transform method. Okay, so we will solve the wave and the heat equations as examples with this Fourier transform method, but this method works for more general equations. Okay, so let u of xt be a function with x taking any real number value and t positive. Okay, here in this function u of xt, we have these two variables, x and t. And the range of x is the whole real line, r, and the range of t is just the positive numbers. So if you remember the definition of Fourier transform, the definition was for functions defining in the whole real line. So this definition suggests to us that we will transform our function u with respect to this variable x. Remember that we saw the notion of Fourier transform for a function f of x. No matter that is called x, could be f of y, f of t, f of whatever function, but with one variable. So here that we have two variables, x and t, we have to choose which variable to transform this into a Fourier transform. So since the range of x is the whole real line, this suggests us to consider the variable x to transform. Okay, so if we fix t, imagine that t is equal to some fixed t, I don't know, 10, 100, whatever, one particular t, then this function u of this variable, which is called x usually, of this fixed t, so now t is fixed, it's not moving anymore, it's not a variable anymore, it's just a number. So this new function is defined in the whole real line. So we can compute the Fourier transform of this function u of the variable, which is called x usually, and this fixed t. And we can compute this Fourier transform for every t, because in principle we fix one, but then at the end of the computation we remember that this fixed t is any arbitrary positive t. Okay, so we can compute the Fourier transform of the function ux of t, where we are transforming in this variable x. So for each t, this is a function depending on x. Okay, by definition, here again, remember that in the previous lecture we saw these two definitions, the Fourier transform and the inverse Fourier transform, and then how to operate with them, the linearity property, and how the Fourier transform acts in the derivative of a function. Okay, with these four ingredients, the two definitions, the two formulas of Fourier transform, plus these operational properties, plus how the Fourier transform behaves with derivatives, with these four things, we are going to solve partial differential equations. Okay, so now here we are using the definition, which, if you remember, has this factor in the front and is the improper integral from -infinity to infinity of the function times the exponential, the complex exponential. Remember, the variable x is here. Okay. We use this short notation just because it's convenient. So it's hat u in omega t. Remember that here, when we have a function of x and we Fourier transform, then the transform depends on the variable omega. At least we are using this notation. And this t, notice that doesn't change because here is meant not as a variable, it's just a fixed t. Okay, so that was our first step. Let's say we have a function u of two variables, x and t. The t is only positive and the variable x takes all the values in the real line, and that's why we choose to transform this function fixing a t, and we transform in the, with respect to the variable x. And that's why we, after transform, we have here an omega, and this is the notation for the Fourier transform of this function u of the variable x and fixed t. Okay. So, since we want to solve PDEs, we need also the Fourier transform of some of the derivatives of this function ux of t. And we saw at the end of the last lecture, we didn't prove it, and we also are not going to prove it here. What we have, but we have these properties of how this function, how Fourier transforming behaves with the derivatives. Remember that we are Fourier transform the function with respect of x. So all the derivatives that are taken with respect to t go out of the Fourier transform. Okay, so if we want to compute the Fourier transform of the derivative of with respect to t of our function u, that's exactly of having the Fourier transform of u, and after that differentiate with respect to t. If we have to compute the Fourier transform of the second derivative with respect of t of our function u, that's exactly the same as first computing the Fourier transform of u, and after that computing the second derivative with respect to t of that function. You can imagine if we have the third derivative of u and we want to compute the Fourier transform of that function, that's the same of first having the Fourier transform of u and then differentiate 3 times with respect to t, and so on and so on. So what we have here is the property that we can, in some sense, the derivatives with respect to t go out from the Fourier transform. Why? You can prove if you want with the formulas and so on, but the reason, the intuition here is that we are Fourier transforming with respect of x, so t doesn't have to do anything here, in some sense. And that's why we have the derivatives outside. So we Fourier transform u first, and then we compute the derivative with respect to t. Quite different when we are differentiated with respect to the variable x, because we are Fourier transforming with respect to the variable x. So if we have the first derivative of u with respect to x, and we want the Fourier transform of that function, then we saw in the last lecture, at the last minute, that we have this factor in front, I omega, and then the Fourier transform of u of x, t in this case, which is this notation here. Okay, if we have the second derivative of u with respect to x, and we want the Fourier transform of that function, we have this factor in the front to the power 2, and the Fourier transform of u in this variable omega and t. If we have the third variable with respect to x and we want the Fourier transform of that new function, we have this factor with the power 3 and the Fourier transform. Okay, and you can imagine how this goes. So with these two main tools of relating the Fourier transform and derivatives with respect to x and with respect to t, so with respect to t is quite easy because just they go out and then we have the Fourier transform of u. And then with respect to t, you have to remember that the Fourier transform affected in this way, with this factor to the power, the order of the derivative, and then we have next to that factor the Fourier transform of u. Okay, again, no proof. You can try to prove it if you want, but we are not going to give the proof. So now we are able now to give the Fourier transform method, and as usual we try to describe it in steps because it's easier to understand and to remember and to learn how to solve a partial differential equation through this method. So step 1, we already commented last lecture that the steps will be something like, okay, first I Fourier transform the problem, that we will see what that means. Second step, after the step 1, we are supposed to have an easier equation. So we solve that easier equation. That's step 2, solving the easier equation that we got from step 1. And step 3 is, oh, well, okay, I solved an equation, but it was an easier one, and also it's in terms on the Fourier transform of u. And I don't want the Fourier transform of u, I want u. So the third step would be the inverse Fourier transform of u, computing the inverse transform of u to get the function that we want, which is the solution u of xt. And those are the main 3 steps. So step 1, we Fourier transform the boundary value problem in uxt, and we get an ordinary differential equation in terms of this Fourier transform in omega t, where the variable will be t. So to make it a comparison with the Fourier, the separation method of variables, remember that the first step of the separation method of variables was also suggesting certain type of solution, which was the product of two functions where the variables are separated. That's why we have this name, separation of variables. And after working a bit with the equation, with the partial differential equation, we get two easier ODEs. Easier in the sense that before learning how to solve partial differential equation, we learned how to solve ordinary differential equations. So this is exactly the same spirit, because we start with the partial differential equation, but after transforming, Fourier transforming, so here we are not separating the variables, now the technique is Fourier transforming the problem, we will get an ordinary differential equation in terms of this new function, the Fourier transform of u in omega t, where the ODE is in the variable t. And this is supposed to be an easier equation, something that now we will know how to solve with the techniques that we learned in the lectures 1 and 2, let's say. Mainly 1. Okay. So, second step, we solve that ODE that we find. We solve the ODE that we got in the first step, and we find the expression of the Fourier transform of u in omega t. But okay, we want the solution u of xt, not the Fourier transform of u in omega t. So as you can imagine, the third step is just inverse Fourier transform u hat u of omega t to find who is u of xt. And these are the key 3 steps that we have to follow to solve a partial differential equation if we want to use the Fourier transform method. Okay. Observe that we assume that all the functions involved in the partial differential equation admit Fourier transform. And here I think I need a D. Okay. So, examples. As I said at the beginning, we are going to solve the wave equation and the heat equation. Okay, wave equation. Remember, maybe it's already familiar for you, the wave equation has this second derivative of t of u, this positive constant, and the second derivative of x here, and these initial conditions. Okay, so first step, we assume that every function involved, u x of t and f of x and g of x, everyone has admits Fourier transforms. So our first step is thinking this as a function where we fixed t and we have x as a variable, and we find the solution ux of t with at the end with the inverse Fourier transform of certain function. Okay, first step, we Fourier transform the problem, which means we take this problem and apply the Fourier transform in each line and see what we get. Okay, so precisely we fix the t and we Fourier transform the problem with respect to the variable x. So here we are. This is our problem. We Fourier transform it, if we can use this as a verb. So in the first line, you see we have the Fourier transform of this function, the second derivative of u with respect to t, and this piece of the other side of the identity of the first line. And now we will use here, and we do that in this line, right? So the Fourier transform of this line, and at the end the Fourier transform of this line. Okay, and now we will use the properties that we know. For instance, this is a number, and we saw that the Fourier transform is a linear functional, so we can put this number outside the Fourier transform. So that's one property. And then we also saw a couple of minutes ago how the Fourier transform is affected by this second derivative with t, which is, okay, since I'm Fourier transforming with respect to x, this second derivative just goes out of the Fourier transform. But be careful, because with respect to x, since we are Fourier transforming with respect to x, we will have a factor here, I omega to the corresponding power here would be 2, because we have the second order derivative with respect of x, and then the Fourier transform of u. So what we have in the first line is what I was saying, using these properties. The second derivative of t appears here, and we have the normal Fourier transform of u. And these are the linearity to put this c square out, and then the derivatives of how the Fourier transform is affected when we differentiate the function. Okay, and then in the second line, we just have the Fourier transform of u in this particular time, 0, and here the Fourier transform of f. In the last line, again, here we will have the Fourier transform of g, and here again we use the property that we are Fourier transforming with respect to x, so this derivative with respect to t just goes out of the Fourier transform, and then we have this new problem. So this is our new problem, which is an ODE for this function, where now the variable is t. This function is the Fourier transform of u in omega t. Okay. And this is supposed to be a problem that we know how to solve. We can compute a little bit here, because this is like I squared, omega squared, so I squared is this minus here, and omega squared is just there. And now I just color in purple the t to emphasize that we have an ordinary differential equation in the variable t. So we have the second derivative of t of this function. Sorry. This constant, because now remember that the variable is t, so omega is just a constant if we think that it doesn't depend on t. And we have here the function and these initial conditions. Okay, so we know how to solve this, because this is an ODE in the variable t, and it's a second order ODE with constant coefficients, so we know how to solve it. And this was step 1. So step 1 was, we have our partial differential equation, we fix t, we Fourier transform with respect to the variable x, and using the properties of Fourier transform, which are the linearity and how the Fourier transform behaves with derivatives with respect to t, which is the variable that we are not Fourier transforming, and with respect to x, which is the variable that we are Fourier transforming. Using those properties, then we end up with this ordinary differential equation for this function where the variable is t. Okay, second step, we solve this ODE and find this function, which is the Fourier transform of u in omega t. Okay, so we need to solve the second order linear ODE with constant coefficients, and we have these guys here because constant, okay, we know that for us omega is not a constant, but it is indeed a constant because the variable here is t, okay? So this is our second order linear equation with constant coefficient, because here we have a 1, and here we have c squared omega squared, which is constant with respect to t. It doesn't depend on t. Okay, so using the characteristic method, the equation method, we can assume that this function has this shape, exponential to the power lambda t, and then as we already know, I leave this as an exercise, you can find that the solution of this equation has this form, this general form, where these are in principle what we used to call C1, C2 in R, the constant of the general solution of the homogeneous ODE. But now we call them A omega, B omega, or C1 omega and C2 omega, no matter the name. But now we need to remember that these are constants with respect to t, but they might depend on the variable omega, because omega here in the whole problem, omega is a variable, but here in this particular ODE, the variable is t. But this constant can depend and might depend on this other variable omega. So they are constant with respect to t. Okay. So we have this this general solution, but of course we need to use the initial conditions, and we have two initial conditions that will help us to find these two functions that we don't know. So to determine these two guys, A omega and B omega, we use these two initial conditions. So for the second one, we have to differentiate with respect to t this expression, which was the general homogeneous solution. So this is minus this constant c omega sine of this guy and plus this constant cosine because it's derivative of this. Okay, so replacing the information, which is this in this line, and then we set t equal to 0, we have these two new lines. So f, the Fourier transform of f in omega should be equal to the solution at t equal to 0. So this dies and this is equal to 1. So we already know that a of omega is equal to the Fourier transform of f. Okay, in the second line, here we have the expression of the derivative, so, and the only thing that we need to do now is to put to set t equal to 0. So now this guy dies, and we have this one here, and that implies that this is equal to the Fourier transform of g, which is written here in the second here. And now, okay, we just do pass this in the other side of the identity, and we get a and b. Okay, here we need to ask omega to be different to 0. Okay, so finally what we found is that the Fourier transform of u in omega t has this form: the Fourier transform of f cosine of c omega t. This is b, the other constant that we found. So the Fourier transform of g divided by c omega and sine c omega t. Okay, step 2 is done already, which was solving the ODE that we got in step 1. The ODE is in terms of the Fourier transform of u in omega t, where the variable is t. So here we have the solution. Third step and last one, inverse the Fourier transform this function u, the Fourier transform of omega t, of u in omega t, so we get the one that we really want, which is u of xt. Okay, so here just the definition. U of xt is exactly the inverse Fourier transform of the Fourier transform of u in omega t. Okay, and now, well, we know who this guy is. It's just the one that we got in step 2, so we just copy that. And here we use the definition of the inverse Fourier transform, which has, we have this factor in the front and the integral between minus infinity and infinity of the function and this complex exponential. Okay, and so far this is what we can do when we get particular functions f and particular function g's. Then maybe we can reduce this expression a little bit more, but so far, for now, that's it what we get. So 3 steps, super clear. The first one, I have a problem, a partial differential equation. I Fourier transform the problem and get an ODE with where the variable is t and the function is the Fourier transform of u. In the second step, I solved this ODE and I found the Fourier transform of u, but I don't really want the Fourier transform of u. This was just to be able to solve the partial differential equation. So the third step is anti-transform this Fourier transform of u to get the real u. And again, we just use the definition of the inverse Fourier transform. Okay, that was the wave equation. Let's take a look at the heat equation, which is we are going to do exactly the same, just with a different equation, the heat equation. So if you remember, the heat equation is this. We have only the first derivative of t, a positive constant, the second derivative of x, and this initial condition. Okay, again, assume that everyone has a Fourier transform, and all, so f in this case, and all the functions u where the variable is there, and t for every t. Okay, so assuming that, we can use this method. So the first step again is Fourier transforming the problem with respect to the variable x, which is I apply the Fourier transform in each line of the problem, and now we use all the properties that we know, again linearity, so we can put the c square out of the Fourier transform. Here we know that we will have a factor I omega square and then the Fourier transform of u. And here we know that this derivative goes out of the Fourier transform because we are transforming with respect to the variable x. So the derivative of t doesn't affect, let's say. And here we have just the Fourier transform of u in omega 0. Okay, so what I just said is written here. The derivative goes out. Here we have the Fourier transform of u in omega t. The c square, because of the linearity, goes out. The factor, because of the second derivative of x, and the Fourier transform of u in omega t. And okay, so we solve here. The I square is -1, and the omega square is there. And this line, which is like the easiest line. Okay. This is an ODE in terms of this function in the variable t. So step 1 is done. Step 2 is solving this ODE. Okay, so we solve the ODE and we get the expression of the Fourier transform of u in omega t. Okay, so we just work a little bit with this equation. Remember, this is the function, but the variable is t. So we rewrite this equation here. Well, you can complete the details as an exercise, which is just a super easy equation that we were working a lot with it. So we have this solution. Here, remember that maybe we used to say like, oh, a constant c in R, like any real number, or c1. But again, now in this context, this is a constant, but with respect to t. So it might depend in the variable omega, on the variable omega. So that's why it's called A of omega, could be called B of omega, C of omega, whatever of omega, but it might have this dependence on omega, not in t, because it's constant with respect to t. Okay, and this exponential is the function, let's say. Okay, so we have one function to determine and we have one initial condition, so we are okay. So to determine this function A of omega, we just use this information, which is our initial condition for the ODE. So the Fourier transform of f is equal to the Fourier transform of u in omega 0, which is just taking our solution, general solution of the homogeneous equation, and setting t equal to 0. So this is exactly 1, and we get this A here. So finally, the Fourier transform of ux of t with respect to x is given by this expression, where we have the Fourier transform of f in omega and this exponential here. Okay, but again, we don't really want this function. It was just an auxiliary technique to solve the partial differential equation, and now we just inverse Fourier transform this to get u. And this is the last step, step 3. So again, by definition, u is exactly the Fourier inverse transform of the transform of u. Because remember, I have a function u, I Fourier transform it, but then if I anti-Fourier transform it or inverse Fourier transform it, then it's like doing something and undoing the something, so the same thing, so I recover the u. Then from this line to this one, what happened is that we just copy what we got in the step 2, which is the expression of the Fourier transform of u in omega t. And then what happens in the other line is that we just use the definition of the inverse Fourier transform of a function, which has this factor in the front and the minus infinity infinity integral of this function and this exponential here. Okay. So that was for the heat equation. Again, if we know more information about this f, maybe we can work a little bit more in the integral, but so far we can leave it like here. Okay, let's continue. Now, we were lucky with the heat equation and the wave equation because they have constant coefficients in the partial differential equation. But let's see an example, a partial differential equation where we have non-constant coefficients. So for instance, just as an example, this is a partial differential equation because we have these two guys here and a function u depending on x and t. But instead of numbers in the front, like multiplying these derivatives, we have, okay, here we have a 1, so it's a number, but here we have a t, which is a variable. So this example is different from the two that we saw before. Let's see what we can do. Okay, so we will apply this technique, which is the Fourier transform method, and we will follow these 3 steps. Okay. So, step 1, Fourier transform the problem. Again, I just Fourier transform the 2 lines. We use the properties. Here we can use the linearity. Here, the Fourier transform of 0 is 0. And okay, so using the properties, remember, we are Fourier transforming with respect to the variable x. So t is a number for this Fourier transform operator, let's say. That's why this t goes out of the Fourier transform because of the linearity. And this plus is there because of the linearity. Then, we are Fourier transforming with respect of x, so we know that the Fourier transform behaves in this way with the derivatives. And since t is not important for the Fourier transform because we are transforming with respect of x, we have the derivative out of the Fourier transform. Okay, rewriting this, we got this ODE. Okay. So remember, now we have an ODE in terms of this function where the variable is t. And here is t equal to 0 as an initial condition. So step 2, solving this ODE and get the expression of the Fourier transform of omega t. Okay, so again, this is an easy ODE. We just have like a first order ODE. We can divide, pass this guy to the other side of the identity. And we rewrite this like as the derivative of the logarithm of this function. then we can integrate this expression and we get this logarithm here and t squared over 2 here, and we keep the constant multiplying, plus a constant that, again, this constant is constant with respect to t, but it might depend on omega. So each time we have a constant, remember that in this step 2. That's why it's called C omega, can't be called A omega, B omega, or whatever omega. Okay, so we get rid of this logarithm applying the exponential function here. So we have this guy, which is a new constant, we call A omega, again, or the name that you want, and this exponential function. So finally, we have this expression for the Fourier transform of u in omega t. Okay, now we need to find who is A of omega, and we have the initial condition for this equation. So we use this initial condition and get, following this identity, this is just the initial condition of the original problem but Fourier transformed, and this is the solution, the general homogeneous solution that we got from the ODE, and this is setting t equal to 0, and we get this A. So finally, last part of step 2, we get the expression of u, the Fourier transform of u in omega t, which is the Fourier transform of f times this exponential. Okay, step 3. We don't really care about the Fourier transform of u. We need u, which is the solution of the original problem. So we anti-transform the transform of u. This is the first line. Second line, we just copy what we got in step 2, the final formula. Step 3 of this change of identities, we use the definition of the inverse Fourier transform, which is exactly this guy here, the factor 1 over square root of 2 pi, the integral from minus infinity to infinity of the function that we got and this exponential. Now we can work a little bit more in this example. In the other example, we were finishing here and said, well, okay, if we have some particular f and some particular g, maybe we can work a little bit more in the integrals, but we just finished in that moment, and now we realize that, okay, maybe I can do better here. So if we rewrite these two exponentials, they have in common this factor I omega, and we have here x minus t squared over 2, okay? Then rewriting this, we have this expression, so this factor as usual, and the integral from minus infinity to infinity of the Fourier transform of f, and this exponential. And this is exactly, if you look at the definition of the inverse Fourier transform of this function, evaluated in x minus t squared over 2, which is this guy here. So now, last observation. I have a function I apply the Fourier transform, so I get the Fourier transform, but then I apply the inverse Fourier transform. So I did something and then I undid the same thing. So here I did nothing, so I have the f. So by definition, well, here is like more notation just to convince you that this is true, but just think about it for a couple of minutes and you will see that this is exactly f at x minus t squared over 2. So what we get is that our solution ux of t is this function f evaluated at x minus t squared over 2. Okay, and I think that's it for today. Let me check. Yes, it is. So today we solved partial differential equations with the method of the Fourier transform method, which consists in these three clear steps. I have a partial differential equation and I have no idea how to solve it. So I Fourier transform the problem, and then I get an ordinary differential equation in terms of the Fourier transform of u, where the variable is t. In the second step, I solve this ODE and I get the Fourier transform of u in omega t. But I don't want that function for real. It was just an auxiliary thing that I'm doing to solve the partial differential equation. So the third step is applying the inverse Fourier transform to get the function that we really want, which is u of xt. In the examples that we saw, the heat and the wave equation, depending on the initial data, maybe we can work a little bit more with the final expression that we got. And in this last example, where the coefficients are not constant, we have in this example a t multiplying one of the derivatives of the function u in the partial differential equation. We could work quite a bit with the final expression and finally get a really nice formula for the solution. Okay, so good luck with the exercise of lecture 8.